series that is involved here is converging because of condition 17, which describes the worst case scenario. So we want it to be positive and converging. That's why these two conditions were necessary. Now that we know what is a type 1 low copula, let's move ahead and find the estimates of parameters lambda k that are involved there. But before we find the estimate, there are some examples that established here. The first example is what we call the sine-cosine copula, which is obtained when we choose the specific basis where we have sine-cosine copulas. They satisfy the conditions given above. They are bounded. And these form an orthonormal basis of 0, 1 squared. So this family of copulas is called the sine-cosine copula, and that's the function given by equation 19. And there is also an interesting case, which is the extended FGM copula. By choosing the basis to be the set of, one is there, and we use rescaled and shifted Legendre polynomials for our functions pk, then this copula constructed by this specific basis under the condition 21 is an extended FGM copula. And it's one example of the type 1 low copulas that we defined in the previous slide. And there is an example that we will be focusing on in the rest of the work in the real life application. Which is the extended FGM copula with one parameter lambda 2, as you can see here. The importance of these copula families, why they stand out is because of one reason. There are several others, but here I will present the one that is related to the maximal correlation coefficient rho star, which is a way to measure how well a copula can describe a dependence. The more it is lower, the more we have a copula that describe more extreme dependencies. And for the FGM copula, the maximal correlation coefficient is 0.4 at the extended FGM copula. And for the classical one is 1/3. So we see that the rho star for the extended FGM is slightly greater than rho star for the normal FGM copula, which means it can capture more dependent structure in the data. So wherever we can use the FGM, we can use this one and it will do a better job. And we will show it in an example. Parameter estimation, as I said, we have parameters that are involved. We need to provide estimates so that we can work with them, right? And we established that for any copula-based Markov chain, U0 till UN, generated by copula 18, which is the type 1 low copula, and the uniform distribution on 0, 1 as a stationary distribution, lambda hat k as given in equation 24 is an estimate of the parameter lambda k. And we established that it's an unbiased and consistent as long as k is finite. If this k is finite here, then we have unbiasedness and consistent, which are two important properties that any estimator should satisfy. And after that, naturally, we will need to determine the distribution. If you have an estimate, the next step is to find the distribution of this estimate so that we can make inference on that. So this theorem is the multivariate central limit theorem. So we assume that we have a vector of estimates, lambda k1 till lambda ks. And okay. So we have this vector of estimate, lambda k1 till lambda ks. And we established that it verifies the central limit theorem given by equation 26. And this equation makes sense as long as conditions C1 and C2 are satisfied, so that we have a finite covariance variance matrix. These conditions are necessary for this to hold. And the components of the matrix sigma are given by equation 27. By equation 27 here. Dr. Clark, I think there is a copy for you here. Oh, sorry. So the components of the matrix sigma is given by equation 27. Here we just focus on where k is different from g, the off-diagonal terms. For the diagonal terms, there is this, the following theorem will give the components for that. So this is the universal limit theorem. When we focus only on one parameter at a time, not all of them, right? So if we focus only on one parameter, under the conditions of the previous theorem, where we assume that we have one parameter, then the limit theorem in 28 holds for the parameter lambda hat k. And sigma squared k is given by equation 29, which describe the case where k equals g in that previous formula. So when k equals g here, we have this sigma squared k, which complete the matrix as a whole now. We established these graphs, which looks easy, but for drawing that was not a simple task. We had to generate a Markov chain with 5,000. The sample size of 5,000, and repeat that 1,000 times to get a confidence interval, and then repeat this process 1,000 times again to get a sample of coverage probabilities. So which makes it a total of 5 billion operations that we couldn't make with our computer. That's why we use the supercomputer resources for the Mississippi state. And we end up having this sample of 1,000 coverage probabilities that we plot here. And you can see that this normal or this bell-shaped curve that is appearing there, this is the empirical distribution. And next to it, we have the QQ plots that confirm that this is following a normal distribution. So the coverage probabilities from the previous theorem. So the coverage probabilities of the confidence interval obtained in the previous theorem are normally distributed, which confirms our results in that theorem as well. So this is a graphical proof of the previous result that it holds. We also considered the maximum likelihood estimation for copulas, and we heavily relied on Billingsley results to establish all the results about the maximum likelihood. And if you consider a Markov chain, as given here, which is generated by equation 18. All right. So the MLE of a vector of estimates, it's given by equation 30 and also the limit distribution of that vector. So we have the limit distribution, we have the MLE. This L of lambda is the log likelihood function based on that copula. And you may ask, before we take this L of lambda, did we make sure that this C lambda is positive, because ln does not make sense if you have negative values or zero values? Well, we already know that it is positive because it's a density of a copula that we already proved in the previous. But to make sure that all the other properties of MLE hold, so that the existence and the uniqueness and even the limit distribution, there are several regularity conditions that has been established by Billingsley that we will not check here, but which we checked in, you can find in the paper that is available online. So we make sure that the Billingsley conditions are satisfied, then 30 holds. We have an asymptotic distribution for our MLE estimate. And we also have a confidence interval given by 32 as long as the components given by equation 33. As I said, this is also a graphical proof of Billingsley conditions, the existence and the uniqueness of the MLE, which is the maximum likelihood. When we draw a function, we have a maximum. Does it exist, and do we have many maximums for the log likelihood concern? So we just took one sample, and we plot the log likelihood functions. These are the level curves of that likelihood functions, and these level curves are representing the the peaks that we have, so this round at the end of the graph or in the center is describing the peak or the very high point of the log likelihood function. There is only one high point, which is this one. For that case, we only have one peak for the sine cosine copula. We only have one peak for the extended FGM copula, which means it is unique. There is no other bumps or peaks in the graph of the local likelihood functions. And it exists because it lies within the region that is appropriate for the local likelihood of the copula.
You don't show the comments, we're not going to get it.
Okay. The estimates, this is the comparison of the estimates and the confidence interval mean lengths. For a small sample size for n equals 100, we have coverage probabilities for our estimate, which is close to 95%. But the MLE is over covering because we have 99.8, which looks great, but for our nominal coverage probability is too high. So it's giving very large intervals, which is not necessary. And when we increase the sample size, it converges to the true value, but it takes more time. So these are the two advantages of our estimate: time saving, and it's very efficient for small sample size. And we also apply that to the bearing data set, which is the application part of that project. So this is the structure that these figures represent here. We have a test rig with 4 bearings rotating on a common shaft. More details are given in the parentheses. The data consists of 2,156 observations, which are collected every 10 minutes. And the output is a 4-dimensional observation at each time point. And the goal is to model the dependence among the bearings. And Ota and Kimura explored this potential dependence by analyzing a portion of dataset number 1 using a 4-variate FGM copula. Now, for our case, we gonna use the extended FGM copula with density given by 34, where we added this extra term here. And functions P1 and P2 are given by equation 35. And the table gives the results of our estimates and the comparison of the AICs, which describe how well the copula fits the data. The extended FGM copula achieved the lowest AICs for 4 of the 6 channels. All those in green are in favor of the extended FGM copula because it has lower AICs, and improving the fit by 2 or 4 units. Only 2 of them are not in favor of the extended FGM copula. Now, this analysis is only taking this data set 2 by 2 because we have a bivariate copula. Now, in the next project, we define a multivariate, let's say a divariate FGM copula that can handle the dependencies at once and can even look at more complex dependencies, like dependence of level 3 or 4, and so on, till dependence of level D. So that's what led to the next project, the extended divariate FGM copula. So what is the extended divariate FGM copula? Start by a definition, a brief definition of that. The extended divariate FGM copula is defined by equation 36, which looks complex, but it's not actually when we have concrete numbers. And the parameters lambda km for k equals 1, 2 satisfy the constraint given by 37, which is necessary for the function given by 38 to be a density of the copula. So for this density to exist and to make sense, we need condition 37 to be satisfied. So if all these hold, then we have a divariate extended FGM copula. And it has PD parameters given by equation 39, which 2 to the power d plus 1 minus 2d minus 2. That's the total number of parameters as long as we have the number d. For example, when d equals 4, the divariate or the 4-variate FGM copula has 22 parameters. And the density can be written as in equation 40, where vk and lambda k are defined by these vectors. So this is lambda top k and this is v sub k that we can replace in formula 40 to get the density of the four varied FGM copula. We also established that any subvector, if you have a vector u1 to ud that follows a d-varied FGM copula, picking any subvector within this vector, let's say from 1 to s, where s is less than d, then it still have the density that is in the same family and with the same parameters, just reduced to the number of parameters that are concerned by that. Now we have this theorem that gives an estimate of the parameters lambda k, which is a more general case. But the thing is, this estimate works for IID case. So we have an IID data set, a simple random sample, so which is drawn from a copula with density given in 38, which is the extended d-varied FGM copula, and uniform marginals to make things easier. So for each integer j, with 2 less than j less than d, and for every subset m in the set of all subsets of B of cardinality J. This is what this MJD means. We select all subsets of B of cardinality J for any fixed J. And the estimator given in equation 43 is the estimates of the parameters lambda K, M. And we established that they are unbiased and consistent with no condition because we are in an IID case. So we don't need to put more conditions on that. Before we establish, after we estimate something, as we said earlier, we need to find the limiting distribution of any vector of that. But before we do that, we need to express the joint expectations of any of the two product of transformation that we have. R and Z could be different, S and T could be different. So how can we handle this expected value given by equation 44? And we use the notations I or Z and I, K or Z because these integrals appears all the time in our expectations and they are the same. So we use these simple notations to make things easier. So 45 is just a notation. Now, following this, we establish the joint expected values depending on the relationship between P and Q. First, we only consider P, and we show that the expected value of the product of the transformations of the random variable that is concerned by it, that is in P, is actually the parameter that is staked to it. Okay, and it's given by equation 46. And we will use this property to show the unbiasedness of our parameter. And the case where P is in Q, which is possible because the cardinality of P is chosen to be less than the cardinality of Q, we have two possibilities. Either P is a subset of Q, or there are some elements in P that are not in Q, even though it's less than Q in terms of cardinality. So 47 and 48 gives the expected values for the specific case. I will take a few seconds to let you read that. So the case P contained in Q also involve the variance because they might be equal. All right, now that we have the expected value of any joint product of these transformations, we can state the central limit theorem for a vector of parameters. So if we consider D to be a simple random sample drawn from the copula, from the D-varied extended FGM copula with uniform marginals, then taking lambda as the vectors of all parameters, no matter what is the order, we just need to use the same order when we are finding the components of the covariance matrix. And with lambda hat as the estimator of that parameter, then we have the central limit theorem in equation 49, which describes the asymptotic distribution of this estimate. And the components of the matrix sigma are given by equation 50. I let you read the details for that. We recall that MP of D is still the subset, the set of subsets of D of cardinality P, and that's what we use to find these components of the matrix. There are consequences that are established using this central limit theorem. The first one is the confidence interval. Naturally, we can get the confidence interval based on the limit theorem that we obtained, since it is normally distributed. But the problem that we have here is we have components in the variance that are not known, but we can replace them by the estimates because we showed that our estimate is consistent. So replacing the true variance by the sample or the estimated variance, it still holds. We can use it to find our confidence interval. And we also define this
Kama kushel.
we also define this test statistic Tn that is used to test H naught lambda 2m equals 0 for all m in MJD. And lambda 2 is the vector of estimator per k equals 2 because we are interested in testing if actually this extension that we define is necessary for a given data. That's why we only base our attention on the subset parameter, which is the parameter where the components are all from lambda 2. And the p-value is given by equation 55, which will help to decide to reject or not the hypothesis. Estimations and tests on the bearing data. Remember the bearing data that we define above this structure. Let me just show it to you for a reminder. So this structure, we still go back to it using the same data set, but here instead of analyzing 2 by 2, we're just gonna take all of them at once using a 4-variate FGM copula. So using this structure, we define 3 data sets. Data set 1, the first half of the data, and data set 2, the last half of the data, and data 3 is the full data set. Tables 2 and 3 display the estimated copula parameters from the extended 4-variate FGM model. So these are the estimates of parameters lambda 2. And all those in green are significant because you have P as statistically significant because the p-value is less than 0.05. Because the normal, I didn't mention that we are using alpha equals 5%. So for our significance level, all these in green are statistically significant. And we can then keep these parameters in our model selection process. And you will also notice that all those parameters that are significant have a consistent estimation. Even we use the dataset number, the dataset 1 or data 2, we have a consistent estimation. Even though the 2 datasets has nothing in common, I mean, they are different, but we see that the model still sticks to the data. That's why it's one way to verify if the copula fits the data that we have. We do the same for lambda 1, and we only, all those in green are significant values. We cannot drop them because they have 0 p-values almost. We have 0 and sometimes 0.03. So they are significant, then we can keep them in our model selection. All those describing 3-level dependence or 4-level dependence are non-consistent and even non-significant for that study. So for the model selection, we consider the density in 56, where lambda 1 star and lambda 2 star are the clean vectors of parameters where we drop all the non-significant values, we replace them by 0. And on the other hand, we consider the 4-variate FGM copula, the normal one, where we consider only the parameter lambda 1, and we assume that lambda 2 is 0 because it's not considered there. So these are the 2 parameters or the 2 models that we will try to evaluate. And we get this table, which reports the archaic and Bayesian information criteria. And we see that the extended FGM copula achieves lower values for both AIC and BIC, indicating a better fit for the data. We have this in green, which means we should have used the extended FGM copula instead of the normal case for our specific data set because it has a lower AIC. But that was not enough to decide if the data, the copula fit the data, because we can also take another model and find an AIC, but it could be maybe lower or greater. How can we make sure that it fits actually the data? But there are several tests that have been established for that. The one we use here is the Rosenblatt transform variables. So we transform each of the random variables of the copula using the Rosenblatt transform methods that I will not explain here. And we also use the Kolmogorov-Smirnov test, which test for the uniformity. So the Rosenblatt transform test assume that if each of the variables that are transformed follows a uniform distribution, then it's actually fit the data. So we see that all these characteristics are in favor of our extended FGM copula. The deviation to the uniform distribution is non-significant, and the p-values are in favor of the uniformity of the data. So that's why we can confirm that yes, it follows the extended FGM copula and it does a better job. And that's all for this second project. And now I'm gonna move on to the last one, which is more theoretical. It's about robust estimation. Which is not using copulas, but stochastic process in general. We don't know their distribution. We don't know the dependent structure. It's just a stochastic process. How can we estimate? How can we get confidence intervals? Things may be easier when we know the distribution or we know some dependent structure, like in the previous two chapters. But in case we don't know that, we need to use robust estimation. The goal is to estimate the mean of mu I, the mean mu I of the process of the sequence Y with finite second moments on the unknown dependence and provide a confidence interval or the confidence region for the vector. Longland and Pellegrin in 2021 proposed a kernel-based estimator using independent noise, and we extend the estimator to multivariate data and apply it to linear regression. Before we state our results, there are a few definitions that we need to present first. The concept of invariant event. So the event A here is said to be invariant if the shifted sequence provides the same, it's still the same event A. Shifting the sequence by K does not change the event A. That makes it invariant. We assume that we have a stationary sequencing at the beginning from a probability space omega fp to the sequence space, which is described by this space R infinity, C infinity, and some measure mu. And the sequence is said to be ergodic if every invariant set has probability 0 or 1. So this condition must be satisfied to have ergodicity. We also use the concept of Quinch central limit theorem and anneal central limit theorem. The Quinch CLT is the central limit theorem that we obtained by conditioning on the past. So this sigma algebra F naught is the past of the sequence. So we can see that the sequence is in Z. So we take all the past, we denote it by F naught. We condition on the past. I mean, if this convergence is almost sure for every omega that we pick in omega, then we have a Quinch central limit theorem for the sum, the partial sum of the stochastic process. And the anneal central limit theorem is the normal one, where we don't condition, it's unconditional. And that's what we use in the previous chapters and the previous projects. The anneal or the Quinch central limit theorem implies the anneal central limit theorem. It's a string result. So proving one is also proving the other. Now, let XSI be an IID sequence, K a kernel, Hn bandwidth a sequence of positive numbers, and we state the condition C1 till C6. They will be necessary for our next result. So I will leave some seconds for you to observe this or read. So if we define Rnk and Rn by equation 59, then we are ready to establish the first result on that general stochastic process. So first theorem, under condition C1 and C6 above, on yi, xi, hn, and k and so this estimator Rn defined in the previous slide is consistent for mu I, and the limit theorem in 60 hold, where C is given by equation 61, and sigma, the general formulation for sigma, is given by equation C. This expected value of y1, y prime 1 is actually a matrix that gives the covariance matrix in general. We applied that result to linear regression. So the model that we consider is given by equation 62, where epsilon ik is stationary, ergodic, and mean 0, pi and epsilon moment as well. And xik is independent across i's and has finite variance, sigma squared. So under these conditions, the least square estimator, beta hat 1k of beta 1k, satisfies the limit theorem given by 63. And the proof of this result uses the concept of quintessential limit theorem, ergodicity, and Slowski theorem. And this results on the linear regression estimate marks the end of our theoretical results. And to summarize, some of our key achievements are that we developed new criteria for psi mixing, psi prime mixing, and psi star mixing in Markov chains. We examined the impact of perturbations and illustrated the theory with concrete examples. We studied the type 1 Long-La copula, derived various estimators along with their asymptotic distributions, and evaluated their performance through a simulation study. We introduced an extended divariate FGM copula and showed on the bearing data that it outperforms the classical divariate FGM copula. And we generalized Long-La-Pelligrad's robust mean estimator to multivariate data. But here we considered that we have the same bandwidth and the same independent sequence for each of the components of the metric. So it's not still generalized. We can still generalize it more than that. That's why one of our next steps is to allow each component of the robust estimator to use its own bandwidth and noise instead of a common choice. Since the type 1 Long-La copula is a perturbation of the independent copula, one or natural direction is to study similar perturbations of other base copulas. These dissertations led to 4 different manuscripts. First has been published already in 2022, entitled On Some Mixing Properties of Copula-Based Markov Chains. We work with Dr. Long-La and Dr. Ngongo Isidore. And the second project is Estimation Problems for Some Perturbations of the Independent Copula, which is under final review. And the third project is an extension of the divariate FGM copula with application, which has been submitted already. And the last project, which is still going on, we expect to finish in the next 2 to 3 months, is the robust confidence region for multivariate means, a generalized random smoothing approach on the dependence. These are the important references that our work heavily rely on. There are more, but these are the most important that we use all the time. And that's all. That's the last slide of my presentation. And thank you for your kind attention. And if there are any questions, I will be more than happy to provide responses. Thank you.
We agree that everything that we did is okay. So for now, what we could think of is to get him some questions. If we have committee members that are here, some are online, we first leave the choice to committee members to interact with the candidate. And after that, if anyone in the audience or online wants him to answer some questions, then we'll be happy to give you the floor. So I think we usually let the audience ask questions, and then we ask questions after. Yeah. We let people go on, and then we have we will discuss it after. So we can ask questions. If discuss the discussion for later. At that time, actually, you will not be here. No, you will. I mean, we usually discuss with the committee and all my give the work to the audience. But if you guys want, then we can try by the audience. All right, anyone in the audience willing to ask Mous-Abou a question? Or online? Mous,
Yeah.
love the presentation.
Okay.
All the materials. This is not my fault, so my fault. There are a couple of us. You might just talk to us. What's just a short kind of explanation. What you mean by the, but they are not specialists with us. Yeah.
Mhm.
Yes, that's what you want. Yes. You talk to him like a human.
I mean, the whole dissertation, or you have a specific question about some part of it?
We could start with the words.
Mhm.
Also
Okay. So copulas are tools. Let's take them as like tools. There are tools that we use to model dependence. You know, in real life, things are dependent, right? For example, if it rains today, there is a high chance it rains tomorrow because the conditions are still favorable, right? So this kind of dependent things that one depend on the other are called dependent events. Now, how strong they are dependent or how weak they are dependent? How can we measure this dependence between the two? Let's say we just take two things. It could be very, very dependent, like one strongly depend on the other, or they are weakly dependent. But we need to have a measure on how to quantify that. And copulas are very useful to do that. That's where we use them. And yeah, I hope I responded. Or do you need more explanations?
Yeah, that's good.
Yeah, so that's actually how they are used in real life.
You define the maximum correlation, right? Maximum correlation.
Yeah, the maximal correlation
Can you
coefficient.
go to the slide?
Sure.
So you define the supremum over measurable function, right?
Let me open it up. Yeah, there are many conditions that sometimes I just skip them because that's not my point actually. I just wanted to I could skip all these and just present these two, but I wanted to give some hint. But they are measurable. They are measurable functions.
But suppose square.
Yeah, square. They need to be, these functions should be able to allow the correlation coefficient to be computed. That's the general condition. They should be chosen so that we can compute this correlation coefficient.
Suppose you have like two random variables U and B, right?
Yes.
And suppose you have to find the correlation of
you have to find the correlation of the copper C. But
Yes.
the number of variable functions are very big, right? Infinite or bigger than infinite.
Yeah.
So how will you compute this correlation if the two random variables you and we are given? What is the practical use? How can you use it?
Concretely, I would love to answer this question, but this is not actually my point. I didn't deeper into that. I just use it to show that, well, this tool is used to account for the dependence measure or account for the maximal correlation coefficient for something, and this is the formula. And I'm not going too deep into that topic because that's not really what I do. Yeah.
Actually, they answered the question straight in front of you. How do you get rose equal 0.4? Lots of options. The problem is the study of mixing coefficients gives you a way to approximate that correlation without having to circle through all those functions. And the job of my area is to provide people who to give that answer without having to go through some to look how to get. For example, the copula that we had there, we can show you that it's 0.4, show you that the other one is 1/3, without having to take any function to tell you.
Is there any other correlation which is better for the copula than the maximum correlation? Is there any other correlation factor?
There are many measures. I didn't present them here because they were not part of, I wanted to keep it short, but there are many with the Spearman row and the Kendall Tau, and we use them to compare copulas within among themselves. Using these various measures, we can choose, well, this copula is better than this one in this scenario or in this other scenario. So there are many tools that we use. I just gave you two, but you can find more. Kendall Tau and Spearman row, and there are many others. Yeah, I will advise you to read the total paper. You will find all the details on that.
Thank you.
Yeah. Yes, Larissa.
Thank you for the very interesting. I just want to follow up with what the first question I was asked you. Can you give me a real life example where I can use it, or where I can use your tools?
All right, real life example. I already presented the real life example, but let me explain it very short. So this product, where is it again? So this test rig is.
There is someone online that is worried that I've been defending for too long. That it's proposing you this.
Yeah, I already took some draft. That's why I have it with me. My throat is already very. Yeah, thank you for caring about me. Yeah, so this test rig is what we use to, we generally have it in various devices, even in motors and everywhere. You have a common shaft on which many bearings are rotating. Okay, now you're interested in knowing, is the degradation of one of them impact the degradation of the other? Or is it the next one, or the third one, or the fourth one? How does this degradation are related so that we can plan more on how to make this thing? So make maybe the first one more resistant or the third one more resistant so that we can handle this degradation effectively, right? So we need to study this dependence. How strong one is related to the other. Is bearing 1 and 2 have a stronger dependence? Is bearing 2 and 3 has a stronger dependence? Or is there any even 3-level dependence, like 1, 2, and 3? They have some kind of dependence that they describe. So describing this independence or this dependence among the 4 things will allow you to prepare more or to be more effective in making this product. I will make bearing 1 more resistant because its degradation will imply that the degradation of 2, which will imply the degradation of 3, and so on. I will make bearing 3 maybe less resistant because I have limited resources. I don't want to make all of them very strong because I don't want to waste money. I want to have the optimum possibility, right? That's why we use copulas. Many other tools are used to model dependence, but copulas have their own way to do it, and they have proven to be very effective in doing that. That's why they gain interest in recent decades. I don't know if I answered your question.
Some time to answer that question. So, popular basically when you have multivariate, when you collect data with several components, and you have no reason to believe that the components that you're selecting are independent. Moreover, you have some beliefs about the distribution of each of the components. You think that each of the components has a distribution that you know up to maybe some constant, and you don't have any reason to believe that the components themselves are independent. In that case, the joint distribution of your data point has to take into account the fact that you don't know whether the components are independent or not. That role is played by the coupler. And the marginal distribution, which are the FG that he was putting inside, that's your belief about the parameter, the coefficient itself, the component itself, and that component might come from this. And then the job of his study and mine is to figure out now, given that I believe the components might come from these distributions, what is the best coupler that would take, that would model the dependence between those components? That makes sense? One of the examples is, so if we take your blood pressure and we take your temperature every 10 minutes, let's say for 2 days, why should I believe that the blood pressure and your temperature are independent if I'm taking them from the same person? But I can think that maybe the blood pressure. So I take those two models and put on it, and then I try to find the best software that model the causation that might be the temperature.
Yeah. So to add a little on what Dr. Longla said, which already explained everything. We usually use the linear regression. If you remember, right, we have maybe the height and the weight. How are they related? We just try to estimate linear regression coefficient. We assume that it's linear, right? Maybe we observe how the data look like, observing the shape, and try to estimate the parameter. This was one way of doing it, right? But the copular tool is generalizing this process. It goes beyond this linear relationship because it's not always linear. It could be a square, maybe a parabola or any other function. But we cannot keep having shape and trying to estimate parameters. So we need to have a general tool that will give you straight away the dependence without having to plot anything. I think so. It should be useful there, but I haven't used any data set from this field, so I will not respond with assurance that they use it. Yeah. Yeah, I mean, instead of using linear regression, use the copulars. But the thing is, their theory is a little bit more advanced. You need to read a lot about it. That's why linear regression is sometimes easier for, yeah. Mhm. Do with what, say again? Yeah, it's used a lot in finance to assess for risk management and all this stuff. We use copulars for that because they are dependent structure. Some of them are Markov chains. And wherever you see Markov chain, copula is just right away because it's used to model the dependence if you have a nice Markov chain which is stationary. So yeah, it's very well used in economics. Yeah. Yeah, Samuel had a question.
Yeah, I wanted to ask a question. The real life situation. I think for the long line, you try to explain.
Just right, yeah.
I'm kind of good now, but I would like to congratulate you for work.
Thank you. Thank you very much.
Thinking of the popular, because when you mentioned the real life, it got my attention. And I was thinking of events that happened in the past and also in the present, how to see how definitely they are those kind of things. So I was figuring out things that happened within the 18th century, the 15th century. This as like I just mentioned, another issue. Can one rely on this to determine if it has identification, it has had some impact on current situations in the 20th century and the 21st century. Can we rely on this?
Well, Sarah, you're doing linguistics. I'm already lost in your question. This is, I would like, I would appreciate if you can summarize like in one sentence,
Okay,
so that it will
he
be
wants
easier
to
for me.
know- he wants to know if somehow events that happened long time ago
Mhm.
can affect the events that are happening now, and your tools can help in studying that.
Well, are these events qualitative or quantitative? Is it are you using numbers for these events, or they are just, well, copulas are not very effective for qualitative data. I have not used them for that. So I don't think they might be useful for you. Instead, we find a way to use them for qualitative data. This could be a way of a branch of research.
Study something of the copula, study something that's not.
Yeah, it should be numbers. Something that we can measure. Yeah. It might be a topic of research, maybe. We can think of using that for
We have a
qualitative.
question from those online. And if someone wants to ask a question, it's better to unmute your microphone because they are on mute. Okay, the silence probably means there is no more question. So we would love to have the candidate interact with the public.
Yeah, please help yourself before you leave. There are some donuts and juice. Oh, you're coming back? Oh, okay. But sometimes people just go and don't come back. But if you're coming back, if you're not planning to come back, help yourself. If you're staying, yeah. Exactly. Everything? Are you good? All right. You're staying?
You know what?
I understand.
Okay.
We also have some other audience online.
Slide C.
Okay, slide 16.
You're gonna go, okay?
Okay.
Actually, no, wherever you did the sign for yours.
Oh, design. That's the first slide, I think.
Wait, sign?
The sign copula?
Yeah.
Oh,
Way down.
for the sign copula. The sine cosine copula, yeah.
So I see a lot of theorems from Dr. Longland in the that you're citing. There are some open questions that you worked on. Sine cosine calculus.
Open
actually
question.
show the central theorem for estimation, the
Well,
estimator and
yeah, we work for this copula family in general, but we presented as a concrete example based on this sine cosine extended FGM and the cosine copula in a finite dimension.
And there are certain technical assumptions, right?
Yes.
On the lambdas. So are those something that you can peck away at and make it less restrictive? Or are those optimal conditions?
Appear in the when we compute the variance, we face these expressions, and to control that, since we have an infinite sum, we need to impose it.
Well, yeah, if it's a variance, then clearly that has to be finite, so that would be clear.
Yeah, I don't know
There are
if,
assumptions before, like I'm looking at an assumption about the summation of the lambdas is less than something.
okay, in the definition.
For the example,
Yeah, for this summation here.
that's what.
Because lambda k is the same for both.
Okay, so I'm asking if they're optimal, like, are these optimal conditions? That's not really open questions regarding.
In general, you can't beat that, but on a specific example, you might combine the function in some way and find the shortcut. When you can combine the sine and cosine that are.
Nangla, we can't hear you. You,
I would say when you can come, let me.
Oh,
can
okay.
use up your sine.
Oh, okay.